let's do magnetic fields, magnetic force on moving charges 6. A particle of charge Q equals 4.6 microcoulombs is moving at an angle of 24 degrees with respect to the y-axis and a speed of 165 meters per second. It passes through a uniform magnetic field of 0.75 Tesla parallel to the y-axis in the xy plane. So for part A, it says calculate the magnitude of the magnetic force on the particle. So let's start off with A. So finding the force is really simple. Really all we have to do is plug our knowns into a formula. So Q, first of all, we're given the charge. It's 4.6 microcoulombs. Now we got to change that to SI units. So convert the micro. You have to get it just in coulombs. The prefix micro means times 10 to the minus 6. So this is 4.6 times 10 to the minus 6 coulombs. My angle theta is 24 degrees. My speed V is 165 meters per second. And my magnetic field B is 0.75 Tesla. So I go ahead, take those pieces of information and plug it into my formula. FB equals QVB sine theta. Now for those of you who have taken calculus and vectors, you would already know that this formula is the same thing as QV cross B. Okay, so cross product is a property, it's an operation that you can perform on vectors. It's like vector multiplication. Just like you can multiply numbers, this is how you multiply vectors. You cross them. So V cross B means V times B times sine of theta in that order, okay? And the order is actually really important, and I'll show you why when we do part C. Okay, but anyways, let's stick with this expression for now. Just wanted to show you that. So Q, it's right here, 4.6 times 10 to the minus 6 coulombs. V is 165 meters per second. And then B is 0.75 Tesla times sine of theta. Just make sure your calculator's in degrees because a lot of times people change it to radians. Okay, multiply those out. You're going to get 2.3 times 10 to the minus 4 newtons. And we're only asked for the magnitude, so that is our answer for A. Okay, for part B, determine the direction of the magnetic force. Okay, so for the magnetic force direction, we're going to have to use right-hand rule, but I have to get a sense of the problem first. So this is a three-dimensional problem. I'm going to go ahead and just sketch here a three-dimensional grid. Just really simple. So I've got my x-axis, my y-axis, and my z-axis. Okay, so let's draw what we're told. Okay, let's see. The charge is moving at, so this is referring to the speed, or the velocity rather, at an angle of 24 degrees with respect to the y-axis. Okay, now remember this is in the xy plane, so 24 degrees with respect to the y-axis, that's like this. And again, it's in the xy plane still, so V. All right, what else do we know? We know the magnetic field of 0.75 Tesla is parallel to the y-axis, so B is essentially going like this. Okay, might as well be the y-axis. Oh, I'm sorry guys, I've been drawing and you can't even see. Okay, so this is our V in the xy plane, 24 degrees to the y-axis. Our B, the magnetic field, is parallel to the y-axis in the xy plane. So like I said, this is it parallel, it might as well have been the y-axis. Now, how do we find the direction? Well, I've shown you a few examples of right-hand rule you can use. We are going to use the right-hand rule here. It is, after all, a positive charge, 4.6. It's not negative 4.6, so we're going to use the right-hand rule. Now, there's a nice method. Usually people learn this method when they do cross product, like this, and this is why I mean the order is important. Okay, so you see how it's V cross B? This is how cross product works. It's a right-hand rule, but you use your right hand, you keep your fingers together and your thumb at a 90-degree angle. So what's going to happen is my thumb, because Q, V cross B, forget about the Q, it's V cross B, that's what's important. This is going to tell me the direction of a vector perpendicular to both V and B, okay? And that vector is going to be F. The direction of the force is going to be perpendicular to V and B. Okay, so what happens is I start pointing my fingers in the direction of the first vector, which is V, and I curl it towards the direction of the second vector, which in this case is B. And whatever direction my thumb points, that's the direction of the third perpendicular vector, in this case, FB. So I'll show you what I mean. You see here we have velocity, it's parallel, well, it's not parallel, it's in the XY plane. So my fingers, let's say I pointed it like this, okay? So it's pointing in the same direction as this vector, right? Now, here's the thing. As my hand is right now, as my right hand is, I cannot curl my fingers backwards to go towards B, right? I have to actually hold my hand like this, upside with my thumb pointing down, in order for myself to curl my fingers towards B, okay? Because we've got V going in this direction and B going like this. So I go, here's my fingers, and I have to curl towards B. So what's my thumb doing? My thumb's pointing down. So because my thumb is pointing down, according to the angle of this picture is the negative Z axis. Okay, so according to the right hand rule, the direction of your force is in the negative Z direction. So again, so take your right hand, curl, start with your fingers pointing in the position of velocity, in the direction of velocity, and curl towards the direction of magnetic field. And ask yourself, what direction is my thumb pointing? Well, it's pointing down. Okay, my thumb's pointing down. That's the direction of the negative Z direction. Okay, so hopefully that's all right. So last part is C. What would the magnetic force on an identical particle traveling at the same speed along the y-axis be? I think, yeah, okay, I missed the B, it's over there. So what's going to be the force? Well, remember, force is QVB sine theta, right? Theta is the angle between velocity and magnetic field. Now, if your magnetic field is parallel to the y-axis, and now your speed or your velocity is also along the y-axis, this means your velocity and your magnetic field are going in the same direction. And if that happens, well, what's the angle between those two things? It's 0 degrees. Well, what's of curiosity here? Well, we use sine theta, right? We multiply everything by sine theta. So if we do sine of 0 degrees, well, that's equal to 0. 0 times anything becomes 0. So we can say that the magnetic force becomes 0. Okay, so because this is a function of sine, and you know how sine theta looks. Sine theta looks like this. So we've got sine theta versus theta. You got 2 pi, pi, 3 pi over 2, and pi over 2. You can see just by looking at this graph that the maximum value for sine occurs at the 90 degree or pi over 2 angle. Okay, so you get the maximum magnetic field when your velocity and your magnetic field are right angles to each other. Okay, and you get the smallest when they're parallel to each other. But anyways, just always remember the graph of sine theta because that's what's of curiosity here. So guys, that's it for this video. I hope you liked it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh. I can't wait to see you guys next time in video 178, Magnetic Force on Moving Charges 7.